Great success. Can you guys hear me? Okay, cool. Well, I'm Adam Murphy, the automation lead for the automation lead for the security team at One Medical. And One Medical is a primary care organization who is implementing both process and technology with the aim of reducing the total cost of care. Well, we're a relatively new security team at One Medical, and we have logs for sure, but they're kind of scattered all over the place, and this diagram really doesn't do the problem any justice. So we have logs, they're all over the place, and when an incident responder needs to go out and piece together the scenario for an incident, they have to go around to all these different tools that have varying interfaces and different ways of accessing that information. So during the course of an incident, this isn't really good for our resolution times, and it contributes to engineer fatigue. So we need to start pulling this all together. Real-time was never an original goal of this system, but as we were developing the prototype, we realized we were pretty close with 3-second event availability at our destinations. But what were our design goals? Well, foremost, we wanted to ensure that there would be a low barrier for adoption. This past fall, One Medical received a new round of funding with the intent of doubling our clinical footprint. So, needless to say, we're hiring. So, everybody's becoming quite busy, trying to meet their quarterly targets, and but we need the help of our sister teams in order to pull this off. They're the ones with the logs. So, when we are fortunate enough to get their time, we want to make sure that we're using it wisely. Ideally, in time, we would have this entire process automated, and the provisioning process itself would generate everything that would be required for integration. So we're not going to know upfront everything that everybody's logging to, so we want to be a bit flexible with our design requirements. So whenever we choose solutions, we want to make sure that they're environmentally agnostic. I'm the only person on the core implementation team at this time, so it's actually in my best interest to offload as much human task as possible. And we definitely have all these logs, and we've structured our project in such a way to kind of get the most bang for our buck, if you will, one, when we're onboarding. So if we have this really easy process of onboarding, plus we start with our highest impact of logs, we're going into mass volume rather quickly, and the system needs to be able to cope. And while we're on the topic of being able to cope, the system also needs to be able to survive failures and protect our data integrity. And storage is cheap, so where possible, we should store everything forever. And since we're a healthcare organization, we need to be mindful of compliance. We do our best to ensure that patient data doesn't end up on our logs, but of course we have to be prepared for that eventuality. So we completed this prototype over the summer. I think it took me about 2 months, give or take, a couple of weeks to pull it all together. This is what our overall data flow concept looks like. So I'll walk through each of these components and how each maps back to our original design targets. So FluentD is a complete and pluggable aggregation system in and of itself. So, and it's also based in Ruby, which makes it pretty environmentally agnostic. You should be able to get it to run anywhere you can get the Ruby interpreter to run. This is also code that somebody else maintains, but even though somebody else maintains it, it's still a lot of endpoints to have to manage. So we're going to have to be good at this. Now, Treasure Data, the producers of the FluentD software, they generate packages for Windows, Red Hat, and Debian bases. They have Docker containers, and it's also available as a Ruby gem. The plugins for FluentD are available as Ruby gems themselves, and the Out Kinesis plugin for by AWS Labs is one of them. So FluentD will buffer and retry by default should upstream connectivity be lost. And it's also highly configurable. It can parse most log types just by default, but in case you run into this custom scenario, you can also use regular expression labels, which is the syntax that they use for transformation. And being highly configurable, a system only has so many resources available to it, so it is possible to configure FluentD into a situation where it would overrun those resources, causing an entire system to lose its mind. So, but since Fluent is highly configurable, there are a lot of options to be able to mitigate these risks. So FluentD also allows us to get into our base message object. So we're going from our unstructured data into our semi-structured data, and our system only requires it upload 4 tags to be in our JSON object. And that is time, which is a valid timestamp, which is parsable by Python's date library, and an event tag, which is a dot notation hierarchical data type indicator, the host name, which is simply where the message came from, and of course, the contents of the message. So let's revisit the diagram just once more so we know where we're at. So talk about Kinesis data streams for aggregation. So once you've worked out the initial clients, this process actually becomes repeatable to the point of being programmatic. And since there's a Kinesis SDK available for most language, that makes it pretty environmentally agnostic. And with AWS worrying about most of the upkeep of the service itself, I only have to concern myself with the data. And Kinesis also stores records for up to 7 days. It's a time-based queue, and the point at which a record ages out is called the trim horizon. And of course, the scaling is just as simple as adding and removing shards. This actually pairs up incredibly nicely with Lambda, which we'll go over more in just a minute. But as you're doing all this, you need to be mindful of how much data you're actually putting in your streams. One of the things you have to be worried about is your throughput limits. And once you start triggering throughput limit errors, it becomes a little bit hopeless. So you want to make sure that your consumers and producers are self-regulating. This took us a little bit of time to figure out because while it's very well documented what these limits are, there aren't really a whole lot of real-world examples on how to do this. And making it a little bit more difficult for us, most of that documentation is about either the core AWS API or something called the Kinesis producer and consumer libraries, which are additional abstractions on top of the API for more usability. But we're using Python 3, and the available SDK is Boto 3, and it makes trying to cross-reference those materials just a little bit tricky. But in time, it did become obvious that all of our producers and our consumers would have to be responsible for themselves. And we actually ran into another issue. Throughput aside, we didn't actually know what our initial prototype data sizes were going to be, so we just started throwing data at our data streams, which is the beginning of the chaos. So we tried scaling our streams, but there's actually a 2 scaling operations limit per day. So while we're trying to balance out our stream and quash all these errors, we can't actually size the stream appropriately to get past it, to learn what our next problems are going to be. But we actually pleaded very much with AWS support, and eventually they gave us 10 scaling operations per day, which solved the problem pretty quick. But some of the problems that we were running into were problems of scale. So we enhanced fan out was a relatively new feature, and we haven't exactly implemented this portion yet, but we are setting up to both develop and test at scale using multiple consumers. So all of our streams are production, but the processors that we attach to those streams are environment specific. This methodology doesn't work across accounts, so we end up provisioning our environments by VPC. So enhanced fanout actually offers us another opportunity as well. Now, we usually transform for a destination, and we write to all of our destinations simultaneously. So why not put enhanced fanout at the start of the stream so that we can create sort of several many-to-one relationships from our sources to our destinations. Now, let's talk about Lambda just a little bit here. So from the last couple slides, you might think that that's a lot of Lambdas to manage, and of course you're right, but it doesn't really have to be. You can worry about the containers, but you can pack all the source into a single file. You'll see here in a moment that we're not really concerned about taking too long to process, but the container itself has the entry point configurable, and you can put environment variables around your container. And as I was mentioning earlier, we scale up and down with shards on our data streams, and the concurrency, or the number of simultaneous Lambda invocations that you can have at one time, scales to match the streams that are being consumed. So this just automatically happens with Lambda. But we also decided that our Lambdas are going to have another function that are going to rate and filter the data for hot storage. So we call this process determining the event's fidelity, and our goal with this mechanism is to focus the data for hot storage, because right now, if we go all the way back to the beginning, like we have data everywhere, and in that data there is going to be a lot of clutter. So we want to spend a bit of time going through and really becoming intimate with what we're collecting. So moving from just the Kinesis API and into a Lambda, the data is actually a little bit different. So there is a trigger envelope around the Kinesis data, and the Kinesis data is the Kinesis envelope is a little bit different as well. Once you get to the actual data itself, it's the same, but that's going to probably trip you up in the beginning if you decide to take on something like this. You can grab a sample object for your development testing from the Lambda UI. So this one was a hard lesson to learn. Capture and handle every error. So if your Lambda fails, it will retry the batch. And this sets the stage for data duplication. Now, there are cases where it is okay to let the Lambda fail, but you have to accept that it is going to retry the entire batch. And not every error is going to be yours. As we were starting to round the corner and really get our errors handled ourselves, the Kinesis service itself started spewing its own internal errors. But as you're, I lost my place here. Right. Okay. And while you're setting up to capture and handle your errors, this is a good point to instrument for debugging. You're not going to you're going to want to know what's happening inside your Lambda, and AWS, unfortunately, is very little help. So you can get some very high-level metrics, but if you want the detailed information about what's going on inside your function, you're going to need to provide that yourself. And also, the Lambda's execution role is going to need to be updated to allow interaction with services like CloudWatch to help collect these logs and metrics. Code. So this is a bit of what I'm talking about with the Lambda function. This is our Splunk PanOS handler, and you can see the very top line is a capture of time.time. And we do something very similar at the bottom, and this is the rate limiting. Our batch sizes are roughly 500 records, which is the maximum put records request that you can have on the Kinesis API. So we only take what we can process in a single call. And the second line down from the top, actually within the function, is the initializing the list of records you're going to post to the Kinesis API. So it's a simple for loop, and we generate this thing called a hash key. Now, hash key gets assigned a couple lines down to this partition key in the record envelope. So as you're building a record itself, you're building an envelope for that record. The hash key determines which shard this record's going to be written to. So for every record, we generate this random hash key to make sure that we're writing evenly across all our shards all the time. Keep going down. So right here in the middle, this is our put records request. And notice I said capture every error, but I'm not capturing any errors that happen with this. So there are some cases where it would be okay for your Lambda for this to fail. So the exception that gets raised from this is actually a core API call. So if this entire thing fails, it's okay to retry the batch. And mentioning processing all the errors. So you check the envelope for the failed record count, and you can continue down. And you notice while failed record count is greater than 0, once you start getting errors in your batch, you want to make sure you process them until there are none left. Because then you would have a partial failure in your batch, and then again, duplicate records, or even worse, missing records. Is that it for this slide? Yeah, that's it for the slide. Okay, so let's talk a bit Firehose just a little bit here. So Firehose scales automatically for the data size, and it simplifies the delivery to destinations, which is why we're considering it. The delivery stream consumers tend to be more adaptable to scaling operations as well. We didn't initially explore this because being in healthcare, go back to the beginning, HIPAA is a thing. So in healthcare, if you have external services that you need to be secure, they need to be wrapped in something called a business associate agreement, or a BAA. And AWS is actually starting to get really good at this, but not everything is on it. Data Firehose was added to the BAA just ahead of reInvent this past year. So now we're starting to look into it. And although we know we just sort of built our own, it makes sense for us to pivot and try to work it in, because we still have a lot of destination issues, and the promise of Firehose sets us up for a better success in, and also reduces my overhead. It also sets the stage for other destinations. So right now, we're just posting to S3 and into Splunk, but this also sets the stage for Elastic MapReduce, Athena, and Elasticsearch as additional tools for our incident responders. And the ETL is still in a Lambda, and it still works the same as in the data streams model, but they make the association directly with the Firehose interfaces instead of setting up the Lambda triggers manually. So from our exercise, if I had to boil this down in just a few data points, I would say that FluentD onboards clients fairly easily. This is why it was made such a big, made such sense for us for our initial onboarding targets. We're standing up like HTTP endpoints, syslog endpoints, Fluent Forwarder endpoints, because this is how we can get the bulk of our data the quickest. Is just making sure that it's just point and go. So data streams, they provide both a reliable transport and a short-term secure storage. One thing I didn't mention earlier is that about the data streams is that it's pretty much like Kafka. So those records do get written to disk, and that storage is encrypted, which makes it even more ideal for this situation. Those producers and consumers definitely need to self-regulate. This was actually one of the biggest time sinks for us, was getting this regulation settled. And of course, handle all your errors and instrument for inspection. This is actually a pretty big undertaking, and starting from nothing or aggregating nothing has allowed us an opportunity to take on a project like this. And what this really is, and some of you may recognize this. this is the beginning of our data science platform. And for those of you who have taken on data science projects, you know that the bulk of what you're fighting is both getting your data and getting it into the right form so that you can feed it into your models. And with that, I will open up for questions. Currently, we only have about 10 gigs of data flowing through the system. Our Splunk license is 20 gigabytes, so we've gone and artificially limited ourselves so that we're forced actually to go back and write all those filters. So not big yet, but next time I present on this topic, we probably will. The question is, are we working with anybody corporate, specifically AWS? So we actually have been working with AWS a little closely, not too closely. They're very interested in what we're doing, especially since it's targeted towards healthcare, and that's a big push for them right now. But I don't know. We haven't talked to them maybe a couple months or so. So our engagement with them directly is kind of cooled off. Yeah, go ahead.
So why did, because you want to do a data science program, and why you didn't just resort to rsyslog, remote syslog all your data out of AWS?
Yeah, so the question is, why not just rsyslog and be done with this? Well, syslog isn't always going to fit on a system. One portion of the system is our Active Directory logs that we're getting, and we could have put a syslog agent on there. But we feel that this is far more reliable because when you fire off for syslog, most of those implementations are generally UDP, even though there are TCP options available. So you're right there at the emit. You're setting yourself up for data loss. So we figured that, sure, we can set up syslog endpoints, but let's try and minimize those unreliable passes so that we can, again, protect that data integrity and not be missing any of our data. Yeah. That it. All right, thank you.